All right, class, so let's take a look at one of the applications of taking a derivative. One thing we might want to take a derivative for is to find out the maximum or minimum of something. So for example, in section 4.4, there's lots of what's called optimization problems. Okay, so it's kind of like the most efficient way of making things, or I don't know, there's lots of different applications, but that's one of them. So here I'm looking at problem number 13. Okay, so the idea here is we have a rectangular poster that's 50 square inches of printing, but then we surround it with a border, 4 inches on the top and bottom, and then 2 inches on the left and right. What overall dimensions will minimize the amount of paper used? Okay, so the idea here is we're going to find the minimum value, and we're going to find the minimum value of the area by taking a derivative of the area. So first we need to come up with an expression for the area. And once we have an expression, we'll take a derivative and set the derivative equal to 0. And that should give us a minimum or a maximum. Okay, so first let's come up with the expression, which is usually the hardest part of these, is taking this word problem and putting it into a mathematical symbols that we can understand and apply calculus to. Alright, so first things first, we have a rectangular poster. Alright, so I drew it height-wise, but there's no reason that you couldn't draw it lengthwise. Okay, and then around this poster there is a border. There's 4 inches on top and 4 inches on bottom, and then there's 2 inches to the right and 2 inches to the left. Alright, so we add on this border, and our new drawing looks something like that. Okay. So now let's figure out where these other numbers are. Alright, we have this 50, right? So that's the area of the inside poster part. Okay, what we need to do is figure out what are the overall dimensions, so of this whole thing, what are the dimensions, so the base and height of the whole thing, that will minimize the paper used. Okay, so we know the borders, but we don't know this width and the height. We don't know those x and y values, so they could be different, so I'm going to label them as x and y. Okay, but remember, what we're concerned with is we know the inside is 50 inches squared. What we're concerned about is the whole thing, including the border. Alright, so this bottom side I'm going to label as x plus 4. The reason that I'm doing that is because there are x inches here from the poster, but then 2 more on the right because of the frame, and 2 more on the left because of the frame. So the whole base, including the border, is going to be x plus 4 inches. And then the height is going to be y plus 8. Alright, once again, y is the poster, but then we got 4 on top and 4 on bottom, giving us a total of 8 more inches from the border. Okay, so the expression for the area of this entire thing, for all the paper needed for this, is going to be base, x plus 4, times height, y plus 8. Alright, now what makes this as a problem here is that we got 3 variables. We got a, x, and y. Now it's okay that we have a here, but we want a to be an expression for area, but only in relation to one variable. Okay, so we got to get rid of either the y or the x somehow. And this is where it's going to come from. Do you guys agree with this? X, sorry, not plus, x times y equals 50, right? Just for this poster part, ignoring the borders, we said the poster part, that inside where all the printing is 50 square inches, and so that's going to be x times y. So what we're going to do now is a little substitution. We're going to say y equals 50 divided by x, and then we're going to plug it in. Okay, so let's do that. So area now is a function just of x, and it's going to be x plus 4 times 50 over x plus 8. Alright, now I'm going to forward out a little bit. That way it'll be easier to take a derivative. I won't have to do the product rule. Remember, the product rule is when you have something times something, then you have that u v prime plus v u prime. Instead, I'm just going to multiply this out. So x times 50 over x is just 50. 4 times 50 over x is 200 over x. X times 8 is 8x. And 4 times 8 is 32. Alright, so here is now an expression for area, and it looks really easy to take a derivative, which is going to be our next step. Because remember, when the derivative equals 0, that's going to give us a critical point, right? And minimums and maximums occur at critical points. Alright, so let's take the derivative. The derivative of constant is 0. 200 over x, so I'm going to think of it as 200 times x to the negative first. Alright, that way I can bring the exponent out front, so we'll have negative 200 x, and then I got to subtract 1 from the exponent, so to the negative second. So that's going to be negative 200 over x squared, right, because that's what x to the negative second means, plus the derivative of 8x is 8, and the derivative of 32 is 0. Okay, so now I have the derivative is, so a prime of x equals negative 200 over x squared plus 8x. And remember, the minimum or maximum will occur when the derivative is 0. Okay, so I'm going to solve this now for x. Excuse me, that extra x squeezed in there on me. My apologies. So now I'm going to solve this for 0, solve it for x when it equals 0. So 200 over x squared equals 8. I'm going to multiply both sides by x squared, so 200 equals 8x squared. Then I'm going to divide by 8, and so I'm going to get x squared equals 25. And then I'm going to take a square root of both sides, so I get x equals plus or minus 5. However, negative 5 doesn't really make sense because remember x is the base of this poster, and so we can't really have a base of a poster as negative 5 inches. So I'm going to ignore the plus or minus. Alright, so x equals 5. So x equals 5 means that the base is going to be 9. And let's figure out the height. So we got to figure out y first, right? So let's take this 5 and plug it in right here. So 5 times y equals 50. We can now see y equals 10. So 10 plus 8 is 18. Alright, so our poster is 9 inches wide by 18 inches high. Alright, and one other quick thing you want to do is we want to make sure that this is not actually a maximum area. Now if we kind of think about it logically, we can kind of think, oh yeah, it's probably going to be a minimum area. But let's do a quick check. And we would do a quick check by making a sign chart for a prime of x, the first derivative. That's where you do a sign chart. The smallest x could be a 0. And then we want to include our critical point, which is 5. And then x could be as big as we want. It would be a really stupid poster if x was really big, because then our poster would end up looking like this. But anyways, I guess it's still possible for x to be really big. All right, but let's test our values. So let's test a value of x equaling 1. So we're going to plug this into a prime, and if I plug in 1, I'm going to have negative 200 over 1. So negative 200 plus 8, that's going to be a negative value, right? Remember when you're doing a sign chart, you just care about negative or positive. Now let's try a value bigger than 5. Let's try 10. Okay, so negative 200 over 10 squared, so negative 200 over 100, so that's negative 2. Negative 2 plus 8 give us positive 6, or positive is all we really care about. Okay, so since the first derivative goes from negative to positive, we know that our area goes from decreasing to increasing. So we know that this critical point is indeed a minimum. Okay, so the dimensions that go along with that critical point is going to give us the dimensions that will minimize the amount of paper used. All right, if you have any questions, please write them down and bring them to class tomorrow.